So what I want to do now is sort of go back. I'm sort of going back to a part of module 15, just to make sure that we've covered this and you can see this. But what I'm going to do is show how we can use the normal approximation for sample proportions. So here's the scenario that we're working under. We're working under the assumption that, so we're working for a candidate that's running for office. And our claim is that a majority of the population favor our candidate. That's the claim that we're working under. Okay. Well, how would we mathematically write that statement that a majority favor the candidate? What does that usually mean mathematically? So we would just want to have a strict inequality in this case, or sometimes you always hear the phrase 50% plus 1. So that idea. So the idea is we're pushing it just above. So if it's greater than, and in this case strictly greater, is this the null hypothesis or the alternative hypothesis? Alternative, exactly right. So our alternative hypothesis is that the proportion would be, the population proportion in favor of our candidate would be greater than 50%. So again, that's just recapitulating this idea here. So a majority of the population favor our candidate. Okay, so that's how we would sort of capture that idea. All right, so the null hypothesis then is just the exact opposite of that. So the null hypothesis then would be that the proportion is less than or equal to 50%. Okay. All right, so far so good, yes? All right. Now, if we pick, so there's no reason to pick anything particular here. Let's pick my favorite critical value. So my choice for significance is always 0.02. I'm happy to explain more about that, but that's what I believe to be a more appropriate value of what people find on the border of noteworthy. So I'm not sure people find something that occurs 1 out of 20 times as something that's noteworthy, but I think most people would agree that there's scenarios in which if they see something occurring 1 out of 50 times that they note it. So, well, let me, I'm talking, I might as well tell you what it is. So here's the scenario I always present people with. Are you surprised when you encounter someone on the street? So you encounter a stranger, are you surprised to find out that they have red hair, naturally red hair? Is that something that surprises you? I think most people would say no. Okay, but here's the important question. Do you notice that they have red hair? Is it something that strikes you as less than common? Most people would say, yeah, that actually is the case. Now, of course, the proportions change from different ethnic background and different ancestral regions, obviously. But generally speaking, in the human population, the gene for red hair occurs about 1 out of 50 times. So in other words, there's 2% of the world population that has red hair. And that's why as something that sort of triggers our attention as to something that we would or wouldn't notice that's why I think it makes a good choice. I'm not sure that's as effective as it is with a value of 0.05, but for historical reasons, that's the more conventional value that shows up a lot. Okay, so let's do the following. Let's draw a sketch of so if this is the value, we can sort of make a sketch of what the critical region would be. So we'd have, if our population of proportions is centered at 50%. So we're working on the null hypothesis. So if the P is 50% or less, I wouldn't be surprised by values here, but I would be surprised by values up here. So there's some region up here where I would be surprised by the values. And again, this area here, that's the area in the region that we've just shaded. All right, here's the information I can give you. So I can tell you that N is, so when I go out and I collect my data, here's the data I actually get. I have N equals 760. And I found that in my sample, 395 were in favor of my candidate. Okay. And that amounts to a p hat of 52 0.0%. Okay, so this is the information from our sample. So again, we put the hat on here just to remind ourselves that this is we're talking about a sample. Okay, but again, p hat, just to clarify, is just 395 over 760, which is 0.5197 and change. So rounding it to 52% is not unreasonable. Okay. Now again, the way I've drawn it here, so the way I've actually drawn this, if I want to calculate the p-value, one way that I can do this, I can ask, what is the probability of obtaining a sample that is greater than or equal to 395 over 760? Okay. Well, let's write out what we would do. How would we actually get this if we were using Excel? So if we were using Excel, we would do something like this. In cell A1, I would enter 50%. In cell A2, I would enter equals square root A1 times 1 minus A1 over 760. Okay, so this takes, so P is 50%, 1 minus 50% is just 50%. I could have just done 50 times 50, but that would have been fine. Divided by the sample size, that gives me the standard deviation for the sampling distribution of the proportions. And then I could just take and turn this into a z-score by doing, oh, pardon me. So I put in my value 395 over 76. That's my p hat. So now I have p hat. I have the population proportion, the average of the distribution of sampling proportions, the standard deviation of the sampling distribution for the proportions. So in A4, I could just use the norm dist function. I need 1 minus because I'm getting the area to the right. Norm dist. Then I would say A3, my proportion. A1 is the mean, A2 and true. And this would return a value of p equals 0.138. And that's one way that we could actually obtain the p-value for this scenario. All right. Now the point is, we use the normal approximation for this. So we use the normal approximation. Okay. No, that's not an issue or anything. It's just an observation that that's what we put into this. On the other hand, the question is, well, do I actually need to use the normal approximation? That's the other question at play here. All right, so now what I want to do is I want to redo the calculation, but let's do the calculation now as a p-value, but using the binomial distribution. So the same calculation using the binomial distribution. Let me do it in blue here. So now I want to ask, what's the probability of getting k greater than or equal to 395, given what we know about our population? In other words, that we took samples of size 760 and we're hypothesizing a proportion of 50%. So again, using this null hypothesis, well, actually, technically in this case, my hypothesis is probably better written this way. My hypothesis in this case is that we actually equal 50%, because I can't really do a less than or equal to this. But this is the information that I'm taking from my null hypothesis to do this calculation. So again, we know that the probability of k greater than or equal to 395, that's the same thing as 1 minus the probability of k less than 395. Which in turn, we know, because k has to be a whole number, is 1 minus the probability that k is less than or equal to 394. And that's where these problems get a little tricky. You have to remember to do that whole number adjustment. So the function in Excel would be 1 minus binom dist 394, comma 760, comma 50%, comma true. And that would give us a p-value of 0.146. Now, again, just to reiterate this is from the, okay, these values come from the null hypothesis. These values come from the null hypothesis. the 394 comes from this value comes from the sample, but we have to adjust it to account for the fact that I want greater than or equal to 395. The true is always, the true is, again, we're always talking about R value or something more extreme. So that's why we have to include that there. All right, moral of the story, how did we do? Well, the real probability is 0.146. The approximate probability we got is 0.138. So with rounding, this is 0.14. With rounding, this is 0.15. So it's not perfect, but it's not so far off. It's not so far extremely off that it's probably not going to cause an issue for our analysis. And even more so because regardless of which of these values we take, if I'm using an alpha of 0.02, here's the conclusion. Our p-value is clearly greater than our alpha. This is true regardless of which approximate p-value I use, which means the implication then is that we fail to reject the null. And if we fail to reject the null, well, that's not so good for our candidate, because if we fail to reject the null, that means 50% or less are in favor of our candidate. So that's probably not the best finding for our candidate. So how would we actually state the conclusion? Well, let's jump back to the flowchart again really quickly. Our claim did not contain the condition of equality, so we're on this path here, and we did not reject the null. So there is not sufficient evidence to support the claim that a majority favor the candidate. I'm going to go ahead and erase some of this so I can sort of put this in here. So I don't really need the p-values here anymore. All right, so what's our conclusion then? So our conclusion is best stated. There is not sufficient sample evidence to support the claim that a majority favor our candidate. Okay, so not the best news. Not the best news for the candidate. Okay, not the best news for the candidate, but that's evident. Now, did we obtain, so if this had been the sample on which the vote had been cast, then yes, our candidate would have won because the sample is more than 50%. Unfortunately, if we're trying to use the sample to infer information about the population, then that's not actually the case. Then we haven't actually achieved that. So if you know that your p-value is greater than or equal to, then you have to do the 1 minus subtraction. If it's less than, i.e. if it's a left-tailed test, then you don't need to do that subtraction.